Hello, everyone, and welcome to this Taoglas and Nordic Semiconductor Partner webinar. Today we'll be talking about cellular antenna certification. Just some quick practicalities before I hand it over. So the duration will be approximately 50 to 60 minutes. So I'll try to do a 40 to 45 minute presentation and a 10 to 15 minute Q&A at the end. Questions are encouraged, but please type them in the top right corner. You should see a questions window, so please type them there. The chat at the bottom is not anonymous and should not be used for questions. I see some people already typing things in the chat. For the questions are anonymous, but please try to keep them relevant to the topic, and we will answer towards the end during the Q&A. If you do have any more questions after the webinar, feel free to go to Nordic DevZone for Nordic-related questions. That's devzone.nordicsemi.com, or you can go to the Taoglas website at www.taoglas.com for Taoglas-related questions. And last but not least, a recording of the webinar will be available at webinars.nordicsemi.com a few days after the webinar. Now I'll hand it over to Patrick Frank, who is Principal RF Engineer at Taoglas.
Thank you very much, Bjorn. As you mentioned, my name is Patrick Frank. I'm a Principal RF Engineer at Taoglas. I've been with Taoglas for over 8 years. I've been in the cellular IoT M2M space for over 14 years. So in that time, I've worked on hundreds or thousands of products and projects, helping customers from all sorts of industries get to market in the cellular world and get past cellular certification. So with that, today I want to go through certain aspects of cellular certification and to help you to understand, give you an overview of what that looks like. So we're going to talk about cellular certification and exactly what we mean by cellular antenna certification, where that falls into things. And then we're going to focus on a couple key aspects of that cellular certification and how to achieve a couple of important parameters of that. And finally, we'll talk about how to prepare your device and your project for certification. Now, just a moment about Taoglas. Taoglas is focused on best-in-class high-performance antenna and RF design with advanced positioning, imaging, audio, and artificial intelligence technologies. Taoglas has unique expertise in integrating and commercializing highly complex technology solutions. We have enabled thousands of successful hardware and software projects since 2004. We have over 90 patents and 120 pending, and over 430 employees globally. And we have customer support located close to our customers with the latest test, design, and support services. Those employees are spread out across 10 locations globally, with many of them including full RF test labs. I myself am located in the Minneapolis location where we have a R&D test lab, and that picture of the chamber in the last slide was from our chamber. Now, I want to start with an overview of cellular certification, and to help give us some context for the rest of the discussion. The first thing to note is that cellular certification, as with any electromagnetic certification, is regional. Every market is different. The Americas are different from Europe, are different from the Asia Pacific regions, and even different countries within their different jurisdictions may have different variations on those things. So note that just everything is a little bit different, and we're going to talk in fairly broad swaths here. Secondly, is that modular certifications actually go a long way towards helping with these certifications, and that's a big value add. And I'll highlight where that fits in on the next slide. And lastly, our host today, Nordic, has a couple of really good references for certification. So if you're looking have a product and you're looking at certifying it, these are a couple of good references to hit up for looking at. The first one is specific for global certification, and the second is an overview of the cellular certification process for an IoT type of device. Now, when we talk about certification, I like to think of this in three different levels and break it down in this way. In this first level, this is kind of the bedrock of everything, is this regulatory certification. This is kind of classically what we think of when we talk about certification. And this is the legal regulatory type of certification where we're looking at governmental bodies such as the FCC or certification regulation type of bodies such as ETSI or Anatel in Brazil, for another example. And they typically have certain things that they're looking for, and really they're typically focused on making sure that your device is playing nicely with other devices. So looking and making sure that your device is not interfering with other devices or systems, and secondly that it's making good use of the RF spectrum. Secondly, they're looking at safety, RF, potentially otherwise. And lastly, they may be also be looking at basic functionality. For example, a GNSS receiver is functioning as it should. And with that in mind, the testing that's associated with this tends to be focused on making sure that these things are adhered to. So spurious emissions is kind of that classic quote unquote FCC style testing. That's really that focus on making sure that your device is not interfering with other types of devices or other systems that may be required. And along the lines of the safety, the classic example is the specific absorption rate or SAR to make sure that the device is safe for use. Secondly, MPE, or there may be other calculations along the lines for RF safety. Another example might be immunity. So your device may be subjected to interference, uh, and then the device may be checked to make sure that it's not creating additional problems. So again, making sure that when it's subjected to interference, it's not creating additional problems. The second level that we're looking at is on top of that regulatory. And again, regulatory is never optional. You must always comply with that, and it does vary based on the jurisdiction. But the second level is what I'm going to call industry cellular certification, and it's really exemplified by this GCF and PTCRB. Their focus isn't on that type of regulatory framework, but it's really more on ensuring that your devices can roam between things. So, potentially roaming between operators, for example. A second focus may be what I'm calling baseline performance measurements. And this is to ensure that there's uh, good quality and in recognizing that the performance has an impact on the network functionality for a cellular case. And again, so with that in mind, the testing tends to reflect that. So an example of this is network interoperability testing. This is the primary focus of GCF, and it's a huge focus of PTCRB as well. And this is really the slice of things where that module certification really adds a lot of value, where that module handles all or most of that network interoperability testing. And so as IoT integrators, we tend not to see that slice of the testing. One slice that you might see is SIM card interoperability. This tends to be required as part of PTCRB testing if you have a SIM card slot, and is it's another type of interoperability testing to make sure that your device can successfully read all SIM cards that it should support. And then the last one is kind of looking at again at that baseline performance measurements. We're going to focus on over the air measurements or OTA measurements. And that goes into the next round, really, where that third layer is carrier certification. So on top of all those other things, some specific carriers, AT&T and Verizon are two examples of this, but some carriers may have additional requirements on top of all these things. And there tends to be a couple focuses. So one is more rigorous network behavior testing, and that is looking at more things like making sure that your device isn't connecting too many times or trying to just continuously connect to the network, and just making sure that your device is behaving well on their network. The second part of this kind of goes back to that baseline performance measurement, where they may have requirements or they may enforce certain performance metrics. And typically, what they're looking at is that OTA or performance. So, OTA performance requirements. And I'm highlighting that as the focus of the rest of this webinar, where our customers are often looking to meet these performance requirements for their devices, and it can take a certain amount of experience and or expertise to do so. So we're going to walk through the basics of what these are and the key components of how you can get your device to meet these requirements. So when we're talking about these OTA requirements or OTA measurements, there tends to be two terms that come up. The first of which is TRP, or total radiated power, and it's a radiated power with a given set input power. And the way that I tend to visualize this is, if you have a DUT, a device under test, a mobile phone is a good example, and you put your device at the middle of this, of a hypothetical sphere, and you turn that device on, that maybe that mobile phone is in a call, for example, and that hypothetical sphere captures all the power that's radiated out of that device, and then you measure that power that's captured by that sphere. That is the TRP, that's the total radiated power. Now, I won't go through all this math down below, but what we see is that this total rated power, especially for cellular devices, is highly dependent on the antenna total efficiency. For, again, kind of focusing on the cellular space, the transmit powers, the conducted powers out of the module, out of the device, is pretty well fixed. If you've ever glanced across the data sheets, you'll see that it's pretty typically at plus 23 dBm, or 200 milliwatts. Now, the flip side of this is total isotropic sensitivity, or TIS. I've also seen this referred to as total radiated sensitivity, kind of to correlate to that T, total radiated power. And this is, if you have the same device under test and that same hypothetical sphere, if instead of the device transmitting to the sphere, if we have the sphere transmitting back to the device, that's our TIS, and the value of this is where you cross some particular threshold. That tends to be a bit error rate or a throughput, for example. And what we see is that naturally this is dependent on antenna total efficiency, just as TRP is. But TIS has an additional parameter where it's also highly influenced by interference. So that will be our third section of this webinar, where we'll talk about how that works and how to mitigate it. Myself, I find it's always useful to get some numbers, to attach some affirmed concrete numbers when we're talking about these things. So here we have requirements. These are real requirements from AT&T, and if you hit the link down below, you can go to their website and find their actual requirements. They're published publicly. Um, and so there's a few things that I want to highlight here. First is the TRP. If we look at the TRP in the for category 1 and category M1 devices, we'll see that they're identical. And if we look at these numbers, so if you recall a couple slides back, I mentioned a plus 23 dBm uh, transmit power out of the modules. If we take the difference between these, between that and this TRP number, that's the antenna performance that's required. That's the efficiency that we need to achieve for our device in that particular band. For this low band, we see that it's about minus 5 dB, and for the high bands, we see that it's about minus 3 dB, or 50% and 32%. Looking at the TIS, we see that there's some difference, largely driven by the difference between Cat 1 and Cat M1. And this, again, is largely driven by, we see interference. The other thing that I want to point out this small form factor. So this uh, is a classification of devices that AT&T has created and is unique to AT&T. Um, Other carriers may have their own variation on this, but this varies by carrier. As with all of these requirements, can vary by carrier. So that's an important point to note is always go talk to your carrier to get these to get know what your requirements should be. But for this small form factor device, you'll see that these requirements are quite a bit different. They're about 8 dB different here. And this is a recognition that for small devices, and they have a definition here of 107 millimeters, um, they may be challenging to meet the typical performance requirements. And it's important to keep all this in mind with where your device will typically be operating, whether it will be in urban areas or in remote areas and that kind of thing as you look forward. It's really this, you have to consider uh, the implementation of your device. Okay, kind of making note of what these antenna performance requirements were looking like. That's a good segue into looking at antenna integration. How then, if you know what your antenna performance needs to be to achieve a particular TRP, how do you go about doing that? What are the key aspects of that antenna integration? There's a few key metrics, a few key inputs to that. The first and foremost, really is ground plane length. When we're talking about that, we're talking about the length of the middle of this PCB. So we see this area, this length called out here. Secondly is keep out areas. That's kind of like the implementation area of the antenna. And then thirdly is a three-dimensional take on that, a three-dimensional proximity to metal. So knowing that the ground plane length is a primary driver of this performance, here we'll illustrate that a little bit more. So in this example, we have our PA710 antenna with our DSGP18A surface mount GPS antenna connected together with the Nordic NRF 9160. And over on the right, we see the radiated efficiency of our PA710 on these specific examples for these three different lengths. If we'll note this, so down here is our low frequency bands, and up here are the high frequency bands. And you'll note that as we decrease the size of the ground plane, the length of the ground plane, we'll see that the efficiency in the low band in particular decreases. And if we were to continue to decrease the length of the ground plane, we would see that that efficiency would continue to decrease. The second thing that we see is that the bandwidth decreases. So this is a little harder to see, but this left side of this efficiency is pulling more to the right, potentially decreasing more than on the other sides. So that's this bandwidth is just decreasing along with the efficiency. Now, what's our target? What's the ideal for this? What should it be? That's 107 millimeters in this particular case. in general, it's a quarter of the free space wavelength of the lowest frequency of operation. So here it's around 700 megahertz, and that equates to about 107 millimeters, which is that number that AT&T was using for defining that small form factor device. So that's our target. And if you were to have a lower frequency, if you were to use the 600 megahertz bands, that number gets larger. So when we're designing a board mount antenna, we have to not only design the item, the antenna that gets placed onto your PCB, but we also have to design the area, the implementation area directly around the antenna. And we call that the keep out area. And our anticipation is that in that area, so in this uh, zone here, your device will comply exactly with that. In particular, that it's mostly clear of metal, uh, except where we define it. So it's really expecting that, right? It's the antenna is not just this piece that goes onto the board. It's really this whole implementation area, and that's really required for the basic operation of the antenna. And that's really not just a two-dimensional thing, that's a three-dimensional concept. So if we look at that keep out area, we we see that we really need to keep a clearance from the antenna in three-dimensional space. So here we have a simulation of our PA710 antenna. So just as we saw in the previous slides, on its normal evaluation board, uh, where we've placed it close to a large piece of metal that could be a display, for example, or a battery maybe. And we've moved that progressively further away. And there's a couple things to note. The first is that we see in when it's very close, we see a lot of coupling between the antenna and that big piece of metal. This green area is excited surface currents. So we see that those that power is coupled to the metal rather than radiating it. So therefore, we see that effect on the efficiency down below. We see a decreased efficiency, particularly in this low frequency band. And then as we move that piece of metal and the antenna away from each other, we see both less coupling and more efficiency in the low band. So generally, we don't want to see this kind of implementation, right? So even if you have the proper size ground plane and you have the keep out area on your PCB is exactly as we prescribe, if you put it right close to a large piece of metal, that can have a very detrimental effect on the efficiency. So have ideally in this case, you would have this antenna moved up away from this large piece of metal. Now, after you have the antenna, you have your prototypes, you may look at impedance matching. And really, even when you're doing the design, ideally you have all your transmission lines and everything between the modem and the antenna that is all impedance matched. But you gotta get your prototypes and you want to check the impedance match of the antenna. There's a couple points to make here. So one is that we here we show the loss, what we call the mismatch loss, from a given return loss. And so this mismatch loss is loss in that total efficiency that we see. That drives the TRP, from just strictly from an impedance mismatch. And one of the things that's the industry has found over the years as device sizes have continued are always pushed to a minimum, and the number of frequency bands that we have to support is increased only over the years. That the trade-off has generally been that our return loss isn't as good. Our impedance match just cannot stay as good as it could with fewer frequency bands or larger devices. So The target in for a narrowband antenna might be 10 dB. This is kind of that stereotypical target that you might have. Really, it's moved up to 6 dB quite often. That's about a 1 dB increase in mismatch loss. Going actually to the lower frequencies, going down to 600 megahertz, may mean a further trade-off in that return loss. The second thing to note is that after a 10 dB, so if you have a better than 10 dB return loss, there's a pretty diminishing returns from that. And so if you have significant TRP problems and your return loss is already at 10 dB, there's something else going on. You're not going to solve it strictly through additional or improved impedance matching. Now, impedance matching is a deep and rich topic in and of itself, but just a couple thoughts on this, just to help you get started. For cellular devices, they tend to be of a dual band nature, so they tend to have low band and a high band, or low bands and high bands. And the traditional L match is a single frequency band type of, or narrow band type of impedance match. And so you may not be able to use a single L match to achieve the impedance match in both bands. So here's just one potential concept for almost simultaneously and independently matching both high and low bands. So this can be a relatively simpler way to achieve that impedance match. Now, if we look at all of those previous concepts, so if we know that as we decrease the size of the antenna, that the both the efficiency and the bandwidth shrinks, and also recognize that we just have continuously been pushed to support more and more frequency bands. There's a relatively new concept that's come into the industry of this dynamic tuning. Um, so if we think about this as if we know what particular band we're operating on at any given moment, and if we have a way to electronically and dynamically change the impedance match or the tuning of the antenna, then potentially we can put those two things together and have a control loop and dynamically tune the antenna to optimize it for the band that we're operating on. And here we have an example of this. So from our PCS 50 antenna, which is what we call an aperture tuned antenna. Here we have a block diagram for how this basically functions. And down below, we see the return loss, and we see that it has pretty narrow resonances, but there are multiple ones depending on the switch state. So I'm excited to show this as being implemented on a forthcoming Nordic Thingy 91, where the Nordic NRF 9160 supports this type of control loop, and our PCS 50 supports this aperture tuning. So we have this connected together for a Thingy 91 device coming soon to implement this type of dynamic tuning. This is very exciting. Now, that's the antenna integration side of thing. And we saw that the TRP and TIS were both dependent on the antenna performance. But the TIS had that additional parameter, right? It had that additional input of interference. So this works by the mechanism at work here is that there may be some sort of circuit on your device that's creating electromagnetic noise. You could also call that electromagnetic interference or radio frequency interference. It's all the same thing here. And that noise or interference is radiated from your device, from the circuitry on your device. It's being received by its own antenna, its own cellular antenna, which is then interfering with the cellular radio. And so we call this self interference. And the key thing that I want to highlight here is that this is an EMC issue, right? Electromagnetic compatibility. And so what we're going to talk about are all EMC types of concepts and can be mitigated using all the same methods as described in EMC literature. The only difference here is that we're looking at this for a specific bands for specific radios, and that the power levels are significantly lower than what you might see in that traditional EMC case. But all the mitigation methods are come from the EMC world. So just like in the EMC world, we can break the types of interference, the types of noise down to narrowband and broadband. Narrowband comes from periodic signals. Here we have a 25 megahertz square wave that generate harmonics, and those harmonics look like continuous wave types of interferers. The second type, broadband, um, it can often come from a high-speed data bus or a switch mode power supply, and it doesn't look like a narrow band or continuous wave type of interfere. It really looks like thermal noise from the receiver's perspective. It really can't tell the difference between just regular thermal noise or a increase in the noise floor and this. So all of the receiver is just degraded by this interference. And this is a particularly pernicious for LTE type systems. I'll show you that on the next slide. And just to illustrate this, switch mode power supplies have become a very common method, a very common in type of source of interference for radio cellular systems lately. And this plot on the right is a real example of this. So this is from a spectrum analyzer, and the spectrum analyzer was connected to a device under test. It was connected to the antenna of the device under test. We disconnected the antenna from the radio module and connected it to the spectrum analyzer. And the device under test was inside a shielded and anechoic chamber. The blue trace down here is with the noise floor. That's with the device under test is off and everything is off. The green trace is what happens when we turn the device on, and all of this noise was due to a single switch mode power supply. And a couple additional things to note here. The first is that these levels are very, very low. This is minus 115 dBm, which is 3 femtowatts if you're keeping track at home. The second thing to note is that it really trails off. This tends to roll off well before 1 gigahertz. So this type of problem, especially when it comes to switch mode power supplies, is almost always relegated to the low frequency bands. Here I have band 12 and band 5 highlighted. This particular case, it was only failing TIS in band 12. Reflecting on that, if we look at a couple of existing technologies, so GSM, GPRS, 2G, and LTE as 4G, and we take those TIS requirements that we were looking at earlier from AT&T, and we look at the technology, we can do a little bit of analysis and estimate what kind of interfere power we have to maintain. So we have to have interference that's below this level in order to meet our TIS requirements. And for a 2G system, it kind of doesn't care if it's narrowband or broadband. Everything, all interference really looks the same. And so way back, when 2G was prevalent, we would tend to focus quite a bit on those narrow band interferers to try to keep those low. But as the industry has moved more towards LTE and 4G, we found that LTE is actually more tolerant of these narrowband interferers, but it's actually more sensitive to broadband interference because of the nature of the OFDM systems. And so that's really that, along with moving lower in frequency, has really led us to see these switch mode power supplies and similar types of things really be a very common issue when it comes to meeting these TIS performance requirements. Focusing on that for a little bit, and again, this is not a comprehensive list of everything that can be done to mitigate this, but these are really the primary things that I see when it comes to um, anticipating this type of noise and interference in your design. And first is really PCB layout. If we look at the switching loops here, I have the two examples of switching loops in this supply illustrated down below. On the PCB layout, we really want to keep the area of those loops minimized, and ideally, those loops are very simple and clean and do not change reference planes. Ideally, in my mind, these loops, all this layout is done on the top or bottom only, and you have a solid ground plane underneath the entire thing. Secondly, plan for shielding this switch mode power supply, especially these highly integrated PMICs that we often come across. And then, kind of along the lines of that first point of kind of keeping those loops small, um, you have to think about that in terms of the frequency range as well, right? A 10 microfarad doesn't work as well at 900 megahertz as it does as at 1 megahertz. So adding high frequency capacitors, even a 100 nanofarad or a 1 nanofarad at both the input and the output can really help to minimize that area over a broad frequency band. Extending this to digital switching noise, which can be narrowband or broadband, depending on the digital signal that we're looking at. Kind of the same kind of concepts. We're looking at the full loop of things, and that includes the power supply and power distribution network. So keeping that impedance low, right? Having local bypassing uh, at your digital the buffers. Secondly, keeping the trace routing clean. Again, ideally, if you have that trace routed on a single layer um, and with solid ground planes underneath, and your layer transitions are very clean and very well managed. Keeping all that clean and simple is ideal. Looking more closely at the shielding, it's good to anticipate having shielding on your device, especially anywhere you have high frequency digital electronics and switch mode power supplies. Have a plan, even if you don't necessarily implement it right away. Anticipate having shields on your devices. Connect them directly to your PCB ground planes and minimize any openings or gaps or apertures that you may have in those. The other thing that I focus on when I see a design is you have, radiation coming from the PCB itself potentially, but potentially just as easily you can have radiation coming from any signal or any interface that goes off the board. So as soon as you have something coming off the board, it can be a potentially larger antenna, effectively a better radiator. So I pay particular attention to these. So for power and differential lines, I tend to look for common mode chokes. For power, I will also look for single-ended filtering, so maybe capacitors and inductors, ferrites, that type of thing. And then for single-ended lines, having resistor capacitor or inductor capacitor filtering directly at the interface can be quite helpful as well. And then finally, making note of the PCB stack up. Here I have three examples shown for 4, 6, and 8 layer, and there's just a few things I want to highlight. First, you'll note that in all three of these implementations, we have at least two dedicated ground plane layers. Secondly, is that those ground plane layers in each of these cases are located immediately below the outside layers. Thirdly, the power plane. So on the 8 layer stack up, we implement a dedicated power layer. But note that it's not by itself, it's directly next to a ground plane layer. And so every time if you ever use a power plane or pour, make sure that it's adjacent to a dedicated ground plane layer. And then finally, make sure all these grounds are stitched together very well, at least at the outside edge, preferably throughout the board as well. And certainly, if you ever have a signal change reference layers, make sure you have a ground stitching via adjacent to that. Now, looking ahead, as you look to prepare your device and your program for testing, just a few tips. First is preparing your device for OTA or RSE testing. Um, this is typical of instructions that we would give to our customers if they were to send a device to us for testing. And really, when you're doing an OTA test, the LTE modems are all uh, built have this capability built in, so they are all capable of doing this. And really, the best is just to turn the modem on and just leave it alone. Don't let it fall asleep. Let it auto register. Just let it do its thing, and that's generally optimal. Um, One other thing, and this what used to be required for OTA testing. Nowadays, it's really more as a backup option for debugging. But it's good to have an option for clean AT command access. So without having to open up the device or have something like this that's very intrusive, but having an option to get to the AT command interface of the modem can be very helpful when if the test lab runs into problems with getting the device connected, that kind of thing. This is very useful. And then lastly, of course, provide written instructions to whoever is going to do your testing for any kind of aspect of the device that they may need to have, such as charging the battery or plugging it in, accessing that AT command access, those kind of things. And then when it comes to preparing your device, your program for certification, if you're looking at this uh, needing to perform OTA measurements, you need to have carrier certification. What you absolutely don't want to have happen is you want to get through, get your devices all ready, have all your injection molds are all completed, your PCB layout is finalized, and your production line is all queued up and ready to go, and then you send your device out for certification testing, and then you fail, right? And that at this point, if you look at all those things that we were looking at for having your device meet TRP requirements, meet TIS requirements, we're talking about pretty significant things like device size and PC, large areas of PCB layout, even PCB stack up, that kind of thing. So the ramifications of fixing that failure at that point can be very significant. What the industry has settled on, been doing this for quite some time now, is this concept of pre-testing or pre-certification testing. That's a shortened form of this testing, kind of focused on getting the most bang for the buck, if you will. And it's a great way, again, to gain confidence or to find problems early in your program. TRP tends to be a pretty quick test, and so you can often just do all the TRP testing. Some test labs may simplify that a little bit to make it go even a little bit faster. And then, but TIS tends to be a pretty long test, and so it can be pretty relatively expensive to do that TIS. But it's still extremely important to do. So what we've settled on is we'll often only test the mid channel as kind of that trade-off. And because most of the interferers are just broadband, this tends to catch the majority of cases, tends to catch those highest risk areas. And then radiated spray submissions is often quite helpful to do. So first is intentional radiator. So you turn your transmitter is on and you look for harmonics of that specifically. That's classically been an issue, especially with 2G. And then unintentional radiator. So this has your radio is off, you're looking at 30 megahertz to 1 gig. This is that classic. quote unquote FCC style testing. And then again, don't wait until you have the device is all completed and everything is ready. Do it as soon as you have a functional unit, even if you don't have all the right materials and all this. Early is better. So to recap, remember that every certification is regional. So know where you're going to sell your product, which markets you're going to go to, and what carriers. Carriers are different. They have their own requirements. If you know what carriers you want to use, go talk to them. Anticipate this TRP. So know that device size is really critical for meeting TRP. And then give volume around your antenna for it to radiate. Know that to meet this TIS, you need to have low emissions. And so anticipate that ahead of time and implement these mitigations ahead of time during your design phase. And of course, test early. Don't wait to the end. Test early as you can. And then finally, reach out to us or Nordic if you need assistance. So with that, I'm going to turn it back over to Bjorn.
Okay, great. Thank you so much, Pat. So I just have a few key takeaways at the end, or a bit more information before we get started with the Q&A. So first off, we do have an antenna integration application note that Taoglas has written. And I'll show this afterwards quickly. We also have a Taoglas Nordic web release, which goes more into the details of why we became partners and what the benefits are, etc. So more of a high-level overview. We also have a Nordic partner program page about Taoglas, and we also have some more guidelines for antenna and RF interface on our Nordic Info Center. And last but not least, on the NRF 9160 DK and Thingy 91 product pages, we do have reference layouts and bill of materials there. So on the NRF 9160 DK, we use a Taoglas GPS antenna, for example. So let me just show just some quick information here. So here we have the antenna integration application note. I would say it goes a bit more into detail on the webinar. So it's a very good tool. And I can actually, I'll provide this as a handout to everyone after the Q&A. So this is very useful to know. Then we also have a partner program page on Nordic on our website. Goes a bit more into Taoglas introduction and what kind of design services they offer. On our info center, we have antenna and RF interface guidelines, so that helps you, just hopefully make it easier to get certified and certification. And I think I just want to mention quickly that we do have one of the links that I sent, one of the main links. I think the NRF 9160 certifications is a very great page. So that does go through both global regulatory, so FCC, CE, etc. It goes through some of that. It also tells you what kind of mobile network operator certification it has. And we also go a bit more into details on security. And we also have this blog post, which I mentioned, which goes more into details on how to certify a cellular IoT device. One more thing, if you want to register for upcoming Nordic tech webinars, if you enjoyed this webinar, just feel free to go to nordicsemi.com/webinars. And like Baha already mentioned, if you need any help, if you have any other questions, just either go to taoglas.com for Taoglas questions or go to devzone.nordicsemi.com for Nordic semiconductor related questions. So